About 2 or 3 times a century, a massive star in our galaxy explodes. The star's core may survive as a neutron star or a black hole, but the rest of it rushes into space as swiftly expanding debris behind a powerful shockwave. As the supernova remnant grows, it sweeps up interstellar gas and gradually decelerates. Yet even thousands of years later, its imprint on the galaxy remains impressive. Exploding stars and their remnants have long been suspected of producing cosmic rays, some of the fastest matter in the universe. Where and how these protons, electrons, and atomic nuclei are boosted to such high speeds has been an enduring mystery. Now, observations of 2 supernova remnants by NASA's Fermi Gamma Ray Space Telescope provide new insights. Because cosmic rays carry electric charge, their direction changes as they travel through magnetic fields. By the time the particles reach us, their paths are completely scrambled. We can't trace them back to their sources. So scientists must locate their origins by indirect means, which is where Fermi comes in. The interaction of high-energy particles with light and ordinary matter can produce gamma rays, the most powerful form of light. Unlike cosmic rays, gamma rays travel to us straight from their sources. In 1949, physicist Enrico Fermi worked out how what he called magnetized clouds could accelerate cosmic rays. Later studies showed that a variant of his method, called Fermi acceleration, worked especially well in supernova remnants. Confined by a magnetic field, high-energy particles move around randomly. Sometimes they cross the shockwave. With each round trip, they gain about 1% of their original energy. After dozens to hundreds of crossings, the particle is moving near the speed of light and is finally able to escape. If the supernova remnant resides near a dense molecular cloud, some of those escaping cosmic rays may strike the gas and produce gamma rays. But electrons and protons make gamma rays in different ways. Cosmic ray electrons do so when they're deflected by passing near the nucleus of an atom. Accelerated protons may collide with an ordinary proton and produce a short-lived particle called a neutral pion. These pions quickly decay into a pair of gamma rays. At their brightest, both types of emission look very similar. Only with sensitive measurements at lower gamma ray energies can scientists determine which process is responsible. Now, Fermi observations have done just that. They conclusively show these supernova remnants are accelerating protons. When they strike protons in nearby molecular clouds, they produce pions, and ultimately, the gamma ray emission Fermi sees. NASA's Fermi has detected gamma rays from many more supernova remnants, but the jury is still out on whether accelerated protons are always responsible and what their maximum energies may be. Nevertheless, the Fermi team has taken a major step, a century after the discovery of cosmic rays, in establishing just where they arise. Something that would satisfy, but certainly not surprise, the original Fermi.
Relativistic spaceflight makes the universe accessible to advanced civilizations, but only to those who go on the journey, not to those who stay home. These designs are probably further from the actual interstellar spacecraft of the future than Leonardo's models are from the supersonic transports of the present. But if we do not destroy ourselves, I believe that we will one day venture to the stars. When our solar system is all explored, the planets of other stars will beckon. Would it be possible for a time traveler to change the course of history in a major way? Well, let's think about that. History consists, for the most part, of a complex multitude of deeply interwoven threads, biological, economic, and social forces that are not so easily unraveled. The ancient Greeks imagined the course of human events to be a kind of tapestry created by 3 goddesses, the Fates. Random minor events generally have no long-range consequences, but some, which occur at critical junctures, may alter the weave of history. There may be cases where profound changes can be made by relatively trivial adjustments. The further in the past such an event is, the more powerful its influence. What if our time traveler had persuaded Queen Isabella that Columbus's geography was wrong? Almost certainly some other European would have sailed west to the New World soon after. There were many inducements: the lure of the spice trade, improvements in navigation, competition among rival European powers. The discovery of America around 1500 was inevitable. Of course, then there wouldn't be any postage stamps showing Columbus, and the Republic of Colombia would have some other name. But the big picture would have turned out more or less the same. In order to affect the future profoundly, a time traveler would have to pick and choose. He'd probably have to intervene in a number of events which are very carefully selected, so he could change the weave of history. It's a lovely fantasy to explore those other worlds that never were. If you had H.G. Wells's Time Machine, maybe you could understand how history really works. If an apparently pivotal person had never lived, Paul the Apostle or Peter the Great or Pythagoras, how different would the world really be? What if the scientific tradition of the ancient Ionian Greeks had prospered and flourished? It would have required many social factors of the time to have been different, including the common feeling that slavery was right and natural. But what if that light that had dawned on the Eastern Mediterranean some 2,500 years ago had not flickered out? What if the scientific method and experiment had been vigorously pursued 2,000 years before the Industrial Revolution, our Industrial Revolution? What if the power of this new mode of thought, the scientific method, had been generally appreciated? I think we might have saved 10 or 20 centuries. Perhaps the contributions that Leonardo made would have been made 1,000 years earlier, and the contributions of Einstein 500 years ago. Not that it would have been those people who would have made those contributions, because they live only in our timeline. If the Ionians had won, we might by now, I think, be going to the stars. We might at this moment have the first survey ships returning with astonishing results from Alpha Centauri and Barnard Star, Sirius and Tau Ceti. There would now be great fleets of interstellar transports being constructed in Earth orbit. Small unmanned survey ships, liners for immigrants, perhaps. Great trading ships to ply the spaces between the stars. On all these ships, there would be symbols and inscriptions on the sides. The inscriptions, if we look closely, would be written in Greek. The symbol, perhaps, would be the dodecahedron, and the inscription on the sides of the ships to the stars, something like Starship Theodorus of the planet Earth.